Hi folks. I just wanted to remind you of the problem. The problem statement, this is 388, so you can go to the, I think you can see it in the textbook, but we had two gears and they were interacting along C on this shaft, and then we had a pulley on B, and I shouldn't say a pulley, it was a sprocket with a loading on point B, and then there was simple supports. There were simple supports at A and D. And so as we go through, right, so this we did in class where we had a force, and that force, the definition of the line of action and this pressure angle, in fact, I can draw it out for you real quick, real time, is if I have two gears and they have a center-to-center line, right? And then there's a line that falls tangent to the two gears, pitch circles, and keep in mind, right, these are the pitch circles. There are teeth that extend above and below, right? So there's a gap below and a tooth that extends above. And so in order to have a constant line of action, we use the involute curve. That's one of the types of gears that has a constant line of action. And that constant line of action is at a pressure angle, and that defines the shape of the gear tooth, and that's phi here. Phi is our pressure angle. A common pressure angle is 20 degrees, and so that's what's defined here, and that is literally the line of action for the force on the gear tooth, that force there. And so if we're trying to consider what the transferred power is, we actually need to consider the tangential force that's being transmitted, because the normal force is entirely absorbed or responded to by the shaft of each gear. And so here, if I think about the tangential, right, and I've exaggerated on this side, so we'll kind of use that one. So my tangential force versus my gear tooth force, so I have my tangential is equal to force cosine phi, and my normal is the opposite. And this, my tangential, is equal to the torque over the radius of that gear. So if my input torque is T and my output torque is TC, then I can say that, well, there's a couple of different things that I can say, but I can certainly say that the tangential, and I usually use a lowercase t for tangential, force is equal to T over R, and the normal force is equal to, right, so I'm going to try to get this F, so I have to divide by my cosine phi, so I'll have T over R sine phi over cosine phi. And so I have a magnitude for my two directions, and if I recall correctly, this is the y direction, and I believe this is my z direction. And so my Ft will be in the negative y, negative z direction, because the force from the gear on from the input to the output is this fourth quadrant vector right there. Now, as a reminder, we can find Tc because the force is the same. I didn't quite draw it the same, but it's the same whether you're looking at the input on the output or the output on the input. And so I can say that Ft equals torque over the radius of the input gear, which also equals Tc over the radius of the output gear. And since I know that R in equals half of the R out, right, I can say then that T R out over R in equals TC, which equals the input torque, and this is R out over half R out, or 2T. And so if that was not 100% clear in class, the torque, the output torque onto this shaft of interest is twice the input torque from assuming a motor or something. And so that's how we dealt with the gear. So that's a nice review of gearing. And then, actually I'll just bring up the picture again. So we took this information and we developed a free body diagram. And that free body diagram, a little bit off the screen, let's see if I can, nope, that's fine. So that free body diagram shows the force in the negative z direction, tangential, the force in the negative y direction, normal. We have TC, which is in the, let's see, the negative x direction, right? It's a moment that points in the negative x. We have TB that opposes TC. We have the force P of the chain on the sprocket, and what's missing on this diagram is AY and AZ, both assumed positive at the second support. Okay, so I developed my 4 equilibrium equations, and so you can see some of the forces in the Y, that should be Z, the sum of the moments about A in the Z, and the sum of moments about A in the Y. And just a reminder, right, so I'm looking in the Z, I'm looking for moments that point my thumb in the Z direction. So P points my thumb in the negative Z, Fn does the same, and dy points my thumb in the positive Z. And if you've never seen a room full of engineers trying to use the right-hand rule on some of these awkward poses, you've not lived. Okay, and so then we have the Y, and here I'm trying to get my thumb in the Y direction, so I have, P doesn't have an effect, but I have Ft, and that's positive, and I have dz, and that's negative. And so I have forces times distance, and again, right, the numbers aren't particularly interesting. We will shove some numbers in at some point, maybe, but mostly I'm worried about process, right? And so we could draw out diagrams. It's not strictly required in this problem, and that would be the next step, right? So if you can't intuitively identify the maximum bending moments, then we should definitely sketch that. So I'll go ahead and do that here, and we can talk about it in a moment. So here, if I look on the y-x plane, I have AY, I have P, I have the normal component of the gear interaction, and I have dy. And so here, my shear would be positive, and here I can assume that, and this is an assumption, right? So perhaps I am wrong. It steps down, and so my slope decreases, and then it steps down again, so my slope decreases more. Nope, this is wrong. I'm going to fix it, and this is actually a really good opportunity to talk about it. Okay, and so the incorrect assumption I had made was that my shear would turn positive again because of this, but no, if my shear steps up to 0, then it's negative, at least between Fn or C and D. And so there are 2 possible curves. If I don't plug in any numbers, these are my 2 possible curves. So if P steps down far enough to make my shear negative, then C moment will be lower than the moment at B, and then it goes to 0. Now, if P lowers the shear but doesn't lower it below 0, then it will continue to climb, and it will be a maximum at C as opposed to B, and then go down to 0. And so those are my 2 possibilities. So I have a maximum moment in the Z direction either at B or at C, and I can see here, this is my MY, my Y direction bending moment. Here I have AZ, because I'm looking in the ZX plane this time, and I have FT, and I have DZ. So here, nothing happens at B in the x-plane, and I get to have a maximum at C and then go back to 0 at D. And so those are my possibilities here for my bending moments. So for this step, I just want to kind of walk through the numbers in the textbook, and so you'll have this page to kind of walk through this yourself if you'd like, but rather than go through all these numbers, the theory holds, and so now let's take a look. We have an applied torque of 100 Newton meters. We have, let's see, I think it's 125 millimeter diameter on the input gear, and then a 250 on the output gear. So we have a 2-to-1 ratio, and so if you calculate the torque on the output gear, we're getting twice the torque on the input gear. And if you calculate the tangential force of the gears, you get that 100 Newton meters divided by half the diameter in meters. So we get a tangential force. The normal force is that, just like I said, times the tangent of the pressure angle, 20 degrees. And so we have a value for both the tangential and normal forces. The torque is going to be 200 Newton meters, just like we said. And sorry, I got lost in the notes because there wasn't a clear spacing here. And so then we can find the force P because it's a function. Oh, I don't think I mentioned this before, but my P, my output force P is a function of the output torque by the radius of the sprocket, which is given as 150 millimeters. And so we now have a force P, and we have our summations, including this summation up here, and now we have the reactions at D, the reactions at A, and so that's our equilibrium solution. Now, they mention, right, that it's either going to be at B or C, and we found that using our bending moments, that it was definitely going to be at B or C. And so the moment at B, we could go through the process of just adding together the moments due to AY and the moments due to AZ, etc. But instead, the bending moment at B, and this is assuming we're looking towards A, so we've cut the bar at B, and we're looking towards A. The bending moment is simply the length of the bar, the axle from A to B, times by the resultant vector at R, which necessarily is perpendicular to the bar axle. And so we get a magnitude for the bending moment at B, and same idea, right? If we cut the bar at C, where I only have to look toward D, I can do the same process, and I can find that they are nearly identical, which means that the slope of my shear force between B and C, or the value of my shear force, is nearly 0 because the slope of my moment diagram is nearly 0, but the bending moment at B is slightly higher. And so now we continue using the bending moment at B to determine the bending stress. So now for bending, when we know the absolute or the magnitude of moment at a point of interest, we can define bending for that point as the magnitude of the bending moment times C over the moment of inertia, area moment of inertia. However, if you look in the book, equation 328 reduces this expression to 32m over pi d cubed for a circular cross-section. And that's just a function of the definition of C and D and I for a circular cross-section. And so now we have an expression for bending stress in terms of moment, which we know, and diameter of the shaft, which we know. So then here, if we look at our torsional stress due to the torque, right, I have the generic formula that it's the torque times the radius over the polar moment of inertia. And equation 338 simplifies this for a solid rod based on the radius being half the diameter and the polar moment of inertia being pi d cubed over 32. And so we now have an expression in terms of the torque at B, which we know, and the diameter of the rod, which we know. Now, this is true in the x, y, or at least it's in the 2D plane, right? Well, 3D plane, but it's not, it's on, let me replace that. It's along the Cartesian axes. There is the statement I was looking for. So these are true along the Cartesian axes, but may not be true for the principal, well, it almost certainly is not true for the principal plane. And so this is not the maximum at those points. And so we have to apply Moore's circle in order to find the maximum within the axle or shaft. So if we define the point of B to be such that we have sigma B in a direction perpendicular to the rod, across the cross-section of the rod, and in the opposite direction it's 0, right? So then if you called it sigma x and sigma y, then we're going to say sigma x is sigma b, and sigma y equals 0. And so we can apply Moore's circle principles 313 and 314 to find the maximum stress due to bending on its principal plane, and then the maximum shear stress. So there's a maximum bending stress, normal stress, and shear stress due to bending. And so we can define those with this definition, or with this identification that sigma b is my x and sigma y is 0. Now I could just as soon draw Moore's circle and then identify sigma max and tau max. I would still have to make this assumption. And then I want to highlight just a little bit of nomenclature that is important for clarity. So this squiggly t is a lowercase tau. That's important. And my torques are always capital T. And this is an English T. So you want to use English letters for torque and force. Stress is almost always in Greek letters, tau here for shear, sigma for normal. And so you want to be real careful to start using this notation, because it is pretty standardized across engineering, or at least across the mechanical engineering discipline. So at this point, I'll share with you the solution, because, again, numbers, not super interesting, but are helpful at confirming you understand. So I said here that the normal stress at B, that's going to be our 32 times our bending moment over pi d cubed, and the shear stress at B, 16 torque over pi d cubed. And so these come out to values, making sure we're using meters in the denominator, in those diameters. And then the maximum normal stress is just what I said. It comes out to, what's that, like 20% more? So that's important. And then the shear stress, similarly, is higher. And this is what we analyze for failure analysis, right? That's what we're interested in for failure analysis, because it will fail at the principal plane. And so that concludes this example, again, of 388. Questions, welcome.